good looking man there. Shadow, everything's. How are y'all doing?
Oh.
Any progress? Feel like you got something back there? Okay.
I need you to find the angle of this.
Yeah, okay, I'll come over there. I'm going to put what most people seem to have drawn. Okay.
So since we know this and this, if we find the angle of this, wouldn't that be the same angle right here? So
It would not be the same angle because it's a shorter.
Oh wait, yeah, you're right. Okay.
So let me see here. General picture, instant picture. A little different when you're doing it on your own, right? Is that kind of what y'all have or no? Yes? Any givens or wants or anything? Okay, 7 feet per second is the speed of the person, right? dx dt? Okay, so we're given dx dt. If we write that, then that means that you need to show me on your picture, on your general picture, where x is. So what's x on your general picture? Between the man and the pole. Right here. This distance from here to here we call x. Good. Right? If this is the distance from the man to the pole, if we call that x, we know how fast x is growing, right? X is growing at how fast he's trotting away. So that's growing at 7 feet per second. That okay? What do we want? dy dt, okay. And have you labeled that? Because you need to label that on your graph. What is that on the graph? From where to where? From the... How fast is a shadow moving along the ground relative to the pole? Which means that we are measuring the distance from the pole to the shadow. That would be y. If you call y the distance from the man to the shadow, then what you're doing there is you're getting the speed of the shadow relative to the man. See, the man's moving, right? And his shadow is moving away from him at a certain speed. But relative to someone standing at the pole, it's his speed plus the shadow speed. Does that make sense? Okay, did someone raise their hand? No? What happened to your picture? No? Okay. Are we all okay with this?
Yes.
Okay, at what moment, if you write down what you want, you try and put down at what moment you want this. So at what here? At x equals 12 feet, right? 12 feet. So that's the instant in time right here. When that x is 12 is when we're interested in, right? Questions? All right, let's just recap. We've got a general picture. It's got a couple of variables on it. The 20 and the 6 never change, right? All right, we've got the instant in time. This is 20, that's 6, that's 12. Great. We know how fast x is changing. We want to know how fast y is changing at the moment that x is 12. So I think we have everything except the equation, right? We need to connect y and x together, and we have to be looking off the general picture. And so this is where the geometry comes into play. How are you going to connect these two values of x and y together? So, yeah, you're going to go to some trig. What trig are we going to use? Let's see. Let me put it right here. I'm going to move that. This is at x equals 12, right? Is what we want there. Well, will Pythagorean work? Don't think it'll work, because then we're going to bring in a hypotenuse. So how about this? This is the hard part of the problem, I think. You have to see two right triangles. There's two of them. There's this one, and then there's the bigger one. You see the two? Okay, so this one is this. This one is the smaller one, all right? Okay, can somebody give me some of the dimensions or sides of this one? 20 on this side, and then this side must be? Careful, don't look at the instant in time. Why? What? No, this is the big one. Right? So this is y, right? That's y, that's 20. Everyone see that one? Okay. Okay, this is the tricky one. This one, this is 6, right? That's the man. What's this side? Y minus x. Because if this distance from here to here is y, and this distance from here to here is x, this is the difference between the two. This is that y, take away the x. So this is y minus x. Now, why did I draw two triangles? Because these triangles have something important in them, right? They are both right triangles. And do you agree that this angle and this angle must be the same? Because look, didn't they both come from that same angle right there? This angle makes the big triangle and the small triangle. So they share that angle. And if those two angles are the same and these two angles are the same, then those two angles must also be the same, right? So you have what are called similar triangles. Similar triangles. And here's where you would have to know something about similar triangles. Anytime you have two triangles that are similar, that means the ratio of corresponding sides must be equal. What does that mean? That means that if you take the ratio of any two sides, ratio meaning a fraction, made out of any two sides of the triangles, it'll be equal to the same ratio on the other triangle. So it's like if I wanted to, there's a lot of different ratios I could set up. I'm going to write them off camera here. Like one thing I could write would be this. I could do 20 over y equals 6 over y minus x. So I'm saying this divided by this must be equal to this divided by this because they are similar triangles. I could have done it the other way around. I could have done the y over 20 equals the y minus x over 6. Right there, I'm doing this over this must equal this over this. There's more. I could do this. I could do 20 over 6 must equal y over y minus x. So what I did there is I did this side divided by that side must be equal to this side divided by that side. As long as they're corresponding sides, you can set up ratios. And there's a couple more I could do, right? Do you agree that all of these equations have x and y connected? Yes. So I just have to pick which one I feel like working with. And I really like this second one because my x and y is on top instead of on the bottom. And if I have to differentiate, I would like to have my variables on top. So I'm going to take that one. Here's my equation. My equation is, let me write it this way. 1 over 20y equals, 1/6 times y minus x. Okay, all I did there was just rewrote the 20 on the bottom as a 1/20th and the 6 on the bottom as a 1/6. Is that all right? That's an equation. It connects y and x together. I can differentiate that now. Right? I'm going to erase nothing. I'm going to just work up top here. So now I have to take the derivative of this, right, with respect to time. So what is the derivative of the left side? What happens to the 1 over 20? Careful, it's attached to the y, right? So it comes for the ride. So I've got 1 over 20 times, now what's the derivative of y with respect to t? dy dt equals, okay, on the other side, 1/6 comes for the ride. And then I'm going to do the derivative of two things, right? The y and the minus x separately. So what's the derivative of y with respect to t? dy dt. And then minus the derivative of x with respect to t. dx dt. There's my derivative. Any questions on that derivative? No? Do I know what dy dt is? No, but I'm looking for it. So I'm looking for that, so I'm happy to see it. dy dt again, I'm looking for that, I'm happy to see it. And then dx dt. I know what it is, it's 7, right? So now I should just be able to plug everything in. So I have 1/20 dy dt equals 1/6 parentheses dy dt minus dx dt was 7, right? Unfortunately, I've got some work to do here. Can I get rid of those fractions? Is there a number I can multiply through to clear out all those fractions? Do y'all not want me to clear the fractions? Do y'all not care? What can I do? 60? Can I multiply both sides by 60? Is that all right with y'all? No? I just don't like the fractions. 30? You want me to do 30? 30 won't work. Let's do 60 over here and 60 over here. What happens on the left? You just get 3 dy dx, or dy dt, sorry, equals, and then this and this becomes what? 10? And then dy dt minus 7. All I'm doing is just trying to get rid of fractions to make my life a little bit easier. Let's distribute the 10 through. 3 dy dt equals 10 dy dt minus 70, distributing 10 through. What should I do now? Subtract 10 dy dt from both sides. Right, subtract, or you could bring the 3 over, it doesn't matter, but then we'd have to move the 70. So I'm just going to subtract this on this side. If I subtract this here and subtract it here, I should get negative 7 dy dt equals negative 70. Oh, nice numbers. Okay. Divide both sides by negative 7. What do you get? dy dt is, what is it? 10? 10 what? Y is measured in feet per second. Similar triangles, right? Similar triangles. Yes?
Cross-multiply the proportions with
Yes, probably a lot easier to just, yeah, what's being asked here is like, you mean like almost, did you like cross-multiply or something? Yeah, and like if you cross-multiply, things become much nicer, and then you differentiate. Doesn't matter when you do it, but all right. So there's something interesting that I didn't even mention that I wonder if anyone noticed. Right here, when we took our derivative right here, this was our derivative step, right? We did our implicit. Did we ever use x is 12? Do you remember the man was 12 feet away from the wall, from the pole, sorry? Did we ever use that in here? Is x in here at all?
yes.
No, not dx dt. Is x in here? No, right? What does this mean?
No matter how fast
Not fast. No matter where he is, it's a constant speed. What is a constant speed? His shadow. This is a little counterintuitive. Because do y'all agree that the further away you get from the pole, the longer the shadow gets? So if you move further, it's going to get longer. So it seems like where you are should be dictating how fast that shadow is moving, but it doesn't. No matter where you are, this person is moving at 7 feet per second. The tip of his shadow is moving at 10 feet per second. So of course, the tip of his shadow is moving away from him, right? But it's moving away from him at a constant speed, regardless of where he is. So if I had asked this question in the very beginning and I said, hey, there's this person, they're walking away from a wall. Do you think that the shadow is moving at a constant rate? Do you think you would have said yes? I don't know. That depends on you. But most people would have said no, I think it's speeding up because it's getting longer.
Wouldn't it be constant in relation to him and not?
Both, actually. It's constant.
Because it would be his speed plus the speed of the shadow, right? Or
His, relative to him, it's moving away how fast? How fast is he moving? 7 feet per second. And then the shadow's moving at 10 feet per second. So relative to him, it's moving away at 3 feet per second. Relative to him. But relative to the pole, it looks like the shadow's moving at 10 feet per second. So it's almost like you have two people racing, right? You have one person moving 7 feet per second next to a person that's moving 10 feet per second. And of course, one's going to take the lead. That's his shadow. All right, we're almost out of time. I don't think we have time for another problem. But speaking of relativity, like relative to the pole, you all, let's have a quick conversation about relativity because it's kind of a fun conversation as you're defragmenting your brain right now. Please try and do the homework for this section, all right? It's going to be fun. So we've all probably heard of relativity, right? Einstein, relativity, all that stuff. What is this section? 2.7, yeah. Try and do as much as you can out of that homework assignment. So trying to explain to somebody what relativity is, there's a lot of different ways that you can explain it, right? I've seen all sorts of things on YouTube, but here's one explanation. I'm standing here, right? Am I moving? No. Relative to what? So I am on the earth, right? Is the earth rotating? So I am moving, right? Relative to the earth. Relative to the center of the earth. So if I'm standing here on the earth, right? I'm standing here on the earth, and the earth is spinning around, right? Well, I'm not at the North Pole, but you get the idea, right? I am moving, right? I am moving. Now, it doesn't look like I'm moving here. Relative to this wall, I'm not moving. But relative to somebody standing over here, on the moon, looking at me, I am moving, right? Okay, so, the Earth is rotating, but it's also going around the sun, right? And the sun is part of the Milky Way, right? And it's a spiral galaxy, and it's moving as well, right? So everything is relative to the position. That's what Einstein was trying to explain. Here's a really good, that's the one I don't really care for that one. This is a good one, though. I still have you for a few more minutes, so sorry. All right. Let's say that I have a ball, okay? You ready? I've got this basketball or something. I'm going to hold it up. Let's say I'm holding it 6 feet off the ground, and I drop it. It bounces, comes back up. And I catch it, and let's say when I catch it, it's now 5 feet off the ground, right? So I had a ball. I dropped it, bounced off the ground, right? It went down 6 feet. And then let's say it only comes back up 4 feet to make our numbers easy. Let's say it comes back up 4 feet, and then I catch it, okay? 6 feet, boom, bounce up. Let's just say for the sake of demonstration that takes 2 seconds, okay? So it takes 2 seconds for that to happen. What was the average speed of the ball? Well, that's going to be the distance it traveled over the time, right? So how much distance did it travel? 6 feet, 4 feet, that went 10 feet, right? It went 10 feet, whoa, went 10 feet, and it took what, 2 seconds? So the average speed was 5 feet per second. Do we all understand that?
Yes.
Yeah, that makes sense? 6 feet, 4 feet. All right, now, if we all agree that it's 5 feet per second, now I'm going to reveal something that I didn't reveal to you before. This experiment of dropping the ball and having it bounce back up was actually taking place. We're not sitting in a room, we're actually sitting on a train going down the train track. What are you going to see? You're in the train with me, what are you going to see? Bounce, come back up. That's what you see, right? And so you're going to say 5 feet per second. But somebody, yeah, no? Yeah, if we're all in the train together, that's what you'll see. But here's the train, right? Here's me in there. I'm going to do that, bounce the ball and do it again. But now you're sitting outside the train and I'm going by. Yes?
It's gonna look like.
What does it look like if you're sitting here and here comes the train and I bounce the ball, it goes like this and it comes back up like that and I catch it, right? That's what you see. So what did it do for you, for the observer? It went down and then back up. Yes? So it went down and back up for the observer that's outside the train. But we already know that this is 2 triangles, isn't it? Right triangles. This distance is what? 6. And this distance is 4. But the ball traveled what? To you, the observer, it went across the hypotenuse and across the hypotenuse. So to you, it actually went further than 6 feet and further than 4 feet. Which means its average speed to you is not 5 feet per second. It's more than that, isn't it? So everything is relative because it matters where you are in the universe. That's what Einstein's saying. All of your computations are relative. Right? All right. I will see you on Thursday. Do your homework, all right? Related rates. Do your best. Come back with questions. And we move on after this. Let me get this out of your way.